So the talk is titled "A Personal Perspective on Cryptography," and so can you. Okay. Maybe I should turn it on. Sorry about that. Yeah. So to start with, I'm really starting at a very large height and then try to focus down on a technical topic. So, but to start very abstractly, there are three types of invited talks. The first, advertise own results or maybe projects or your own cryptocurrency. If you know this quote, then you're old like me, or maybe older kids. It's a quote from The Simpsons from a very long time ago. The second type is where the presenter presents an extended version of a recent paper that they maybe want to push for the next conference or maybe want to motivate. And this can be quite technical. And very little of this is maybe a survey over a string of recent papers. It's still very technical, and it takes some, let's say, it takes a bit of effort to follow those things. And the third thing is maybe the opposite of that, just very abstract musings on future directions of a field or an area. So maybe a summary or like things that you learned over the course of 20, 30, 40 years. And this can be very helpful if you're working cryptographer or a working scientist and you're working on a very specific technical problem right now. And then you hear such a talk and that helps you not at all. And so maybe this is a bit frustrating also. This can be a bit frustrating. So what you get today is actually all of the above, but with a personal perspective. And so in the slides I did prepare, I wrote, please ask questions as well. I'm not sure if this works well with the recording, so ask questions right now, only if you feel comfortable, of course, about asking these questions. But generally, discussion would be very nice, either now or later on. So zooming down a bit, there may be several motivations to do research, to do what you do. And the important thing is that research is, personally, I think research is motivated by whatever makes you feel like you get that fuzzy feeling in your stomach, that feeling of satisfaction that you did something good, you did something interesting. And one of those motivations can be grounded in reality. Maybe you improve reality. You're motivated if you, I don't know, work on a COVID app, or you work on something that cures cancer. And then maybe you're motivated primarily by the effects of what you do. Of course, that can be a double-edged sword in some areas. And in particular, as a cryptographer, as somebody working on security, you should always be, you should think about what you do, about the effects of what you do in the negative sense. Also, I mean, maybe that came out wrong, but you should think about the negative aspects and weigh on what you do. You may be doing something fancy technically, but of course, that can have also catastrophic or negative consequences. Then there's the second thing where you're really motivated, not so much by the application, but it's more like an intrinsic motivation to think about the structure of things. Maybe you're more on the mathematically oriented part of computer science. Maybe you want to improve your inner reality. You want to solve problems. You want to discover structure. You want to discover beauty, maybe. And this is a legitimate motivation, and be proud of it. And that's maybe one of the key takeaway messages of today's talk. I think it is not everything has to have, so really that resonates very well with the introductory words. So today's talk is not so much about the applications, but about theory itself as a motivation. So you do things not because of the effects, which is a perfectly fine and valid thing to do, of course, but maybe you are motivated, like me, primarily by trying to understand the structure of something and try to solve puzzles if you want to. Maybe that sounds a bit like small, but it can really be something, it can also be something fundamental to think about puzzles, about technical issues. And the third motivation, of course, can be ego, status, title, or money. And I guess to some extent, if I'm being honest, then for most people, including me, this does play a role. Of course, you want to be the person who discovers something. Maybe not so much about money in our business, but maybe it's about status or the title. You want to be at the forefront of what you're doing. You want to be the person that does something. And I guess that always plays a role, but it's sad if that is the main motivation for an academic career. And maybe you did something wrong if this is your main motivation for an academic career, because maybe status or title or money, maybe not title, but status or money is much easier to get if you're doing something else. Right, so today I'll mostly talk about the theory insights and what motivates me personally as a researcher, and what kind of problems, and one particular example of such a problem. Different perspectives on cryptography. So now let's zoom in a bit more, and on cryptography in particular. So cryptography can be viewed as a means to an end. So you're looking at things with an application in mind. For instance, the application could be blockchain, in which case maybe it's money, maybe it's a financial motivation, or maybe even less negatively, you're thinking about a financial system which is fair, more fair than what we have today. Or maybe you're thinking about secure banking, you're thinking about secure communication, secure email, something like that. So, but then it's a means to an end. And the challenges there are maybe very different from the ones that are connected to structural insight. The challenges there are to get the final system right, to get the APIs right. Maybe that's a big issue that may be boring from a structural point of view, but that is where much actually fails, and many systems fail in practice. So you want to get the implementation right. For a large system, you want to make sure that people really implement the thing that you had in mind, or that someone else had in mind, and something else. You want to maybe think about concrete attacks or complex protocols. Or you can view it like as another extreme. You can view cryptography itself as a zoo of building blocks. And that's actually how I think about it rather. So you have all these small building blocks like encryption, signatures, zero knowledge, multi-party computation, maybe one-way functions, commitments, all of these like small objects. And then you can investigate the interplay between those objects. Is it possible to construct a signature scheme out of a one-way function, or vice versa? The challenges there are to find the right definitions that capture what we want to express with that particular object, to find the right security definitions, or maybe even the syntax, to get the syntax right, to look at relations between those things, what I just said, like do one-way functions give us signatures. And maybe we think about this in a mathematical way. So we think of this in terms of guarantees and proofs. In some sense, you could think about the whole thing as a security assembly line, where you start with a very theoretical view of these objects, and then at the end of the day, you get a working system. But there's so much work in between. And there's space, of course, for all of these investigations. And it's just maybe also helpful to think about where, if you're working in cryptography, where in that assembly line you view yourself. I personally view myself here. My personal perspective on cryptography would be to design and analyze building blocks, as I said before. Maybe a few more examples about this, or let me talk a bit more about this, what I mean. For instance, as I said, encryption. You can view an encryption scheme as a building block, also fully homomorphic encryption if you're into the fancy stuff. Or you can view signatures as an encryption scheme, as building block. Or maybe also more, this is the first bullet points, or the first objects I mentioned were related to secure communication, but cryptography is much more than secure communication. So you could also think about protecting not communication, but protecting computation. And then you're looking at objects like multi-party computation, maybe zero knowledge, where you convince somebody that a statement is true without revealing that the statement is actually, or without revealing why the statement is true. Obfuscation, which basically means protecting computation in a very direct way by just turning a piece of code into something that is unintelligible. And you could think of it as even more basic objects that allow, or that are universal and that allow you to construct the other things. For instance, one-way functions play a crucial role for almost every cryptographic building block and lie at the heart of signatures, of encryption, and in fact also of many of the other things. So here are a bunch of examples. For instance, one of those questions that I personally find exciting and that lies exactly in that area is, if one-way functions exist, do also signatures exist? Is there a construction of signature schemes from one-way functions? This was a resolved question in 1990, and before that, this was like this was a huge open question. This was one of the first, in the first wave of breakthrough results. And maybe a crazy hard question would be, do there exist one-way functions? We don't know for many things, for many objects in cryptography, whether they exist actually or not in a theoretical sense. Whether asymptotically we do have one-way functions even. One-way functions are necessary for instance, secure hash functions, secure encryption schemes, secure signature, but we cannot even prove that we have a one-way function. We do not know asymptotically if there are one-way functions. We have countless candidates. We have lots and lots of candidates for one-way functions, but we can prove nothing. And this is a crazy hard open question. If you can resolve that, then you have to, in particular, resolve the P equals NP question. I mean, you have to show that P does not equal NP. This is one of the biggest open problems in theoretical computer science in general. So this is like a crazy hard question. It's even harder than proving P doesn't equal NP. A hard question, which is maybe more, let's say, current in the sense of this is really what people are looking at, like what a number of people are looking at right now. This is an open problem, and this could happen basically any moment now. We could have an example, we could have an answer for this question. This is take any reasonable assumption. Reasonable, okay, it's of course debatable what a reasonable assumption is. Something like the hardness of factoring integers, or something like this. Can we prove that if we assume that factoring integers is hard, that obfuscation is possible, secure obfuscation is possible? And this is something that we're just about to discover, or maybe it takes a few more years, but that is a hard open question right now. And again, this is just another example of questions which are relevant in that area. And if I say security, then of course there's again a spectrum of a very pragmatic, practical form of security, or where you ask security, where you ask, is something just secure in is something secure in practice, or where you ask this in a very foundational and theoretical manner. A practitioner might say that it's secure if nobody manages to break it, and that's a completely reasonable thing to say or to state. And what you do in order to argue that something is secure is you just look at the best known attacks and maybe choose your security parameters, your key lengths, so that the best known attacks on that particular object just don't work anymore and they become infeasible. Maybe you choose RSA with a certain key length and then bootstrap everything from there. And this is more prone to updates or security accidents than what I'm suggesting below. For instance, in many cases, people have suggested a complete system without a proof, and then it turns out that this is not this is not actually secure. There are attacks for this. Of course, I'm being a bit unfair by mentioning Telegram here, because Telegram didn't really follow best practices. So there are best practices. If you follow them, that already gives you some reasonable practical guarantee that something is secure and not broken. But first, the Telegram people, they did not follow best practices, and they were broken in a bad way. So don't use Telegram if you want secure communication. A theoretician might say it's secure if there is no algorithm, or there is no efficient algorithm maybe that breaks it. So that is, again, like the more introverted way to think about it. It doesn't really care about what happens in practice, because then someone will have to choose the parameters so that everything works out. But you want to prove something that is an asymptotic statement and something that says there is no efficient algorithm that breaks it. There's no asymptotically efficient algorithm that breaks it. And this whole view relies on security reductions, proofs, and assumptions, and tries to relate the security of a given object to an underlying assumption, something like factoring large integers are. This is more robust in some sense, but it's also much less efficient in terms of the constructions that we have which fulfill this kind of properties. And it all right now, realistically speaking, the best that we can do in this area, in this theory area, is still to rely on hardness assumptions like the hardness of factoring that may be broken. If tomorrow somebody finds a proof that P equals NP and finds an efficient algorithm for 3-sub, let's say, then it's much worse than if a quantum computer were around. Then most cryptography will be broken. Not all of it, but really most of it. And in a very, very bad way. And then no reductions of proofs or assumptions. Well, assumptions are violated by that, of course, but it doesn't invalidate any reductions of proofs. They only say that if there is a one-way function to start with, then we can build security out of it. But there is this crucial assumption. So what I'm going to talk about here are security definitions and guarantees, but it's a choice. You can have a very different view on cryptography and about secure systems. It's maybe also just to talk about what this talk is not, this slide. So here's an abstract example, and now it gets a little bit technical, not very technical, but it's hopefully still very understandable, but gets a little bit technical. So what is a hard problem? So when I say hard problem, I'm assuming that there is a problem P that has instances X, solutions S. These are just sets, such that no T-bounded algorithm A can solve a random P instance X with probability bigger than epsilon. So that means just it's a quantitative way of saying that we have a problem, and I have examples, or one example right here. For instance, the instances can be large numbers, and the solutions can be, or the solution in this case, the unique solution can be the factorization of that large number. So that is a candidate that is very popular in cryptography, in fact, and it just says that here we have something that allows us to express hardness of computation in some sense. And such problems are the source of security guarantees. So let's say we have one of those. And T and epsilon are just quantitative parameters that say there is no way in time or with resources less than T, or at most T, to break this problem with a probability larger than epsilon. And these can be just numbers. So the visualization is this. Again, it's very simple. So for any algorithm A that is T-bounded, that spends only resources, let's say runtime T, the probability that this algorithm given X can open, or it's visualized as a box, can find a solution in S, is at most epsilon. So I hope that's still everybody's on board here. Okay, so one exciting thing about cryptography is that we're not usually looking at one of those problems or one of those instances of those problems. Usually you're looking at things where you have many users, you have many ciphertexts, maybe you have in a practical scenario even billions of ciphertexts and billions of users. You're looking at a setting where you don't have an algorithm that tries to solve one instance of a problem. You're often looking at an algorithm that tries to solve many instances, or one of many instances of a problem. So typically, from an abstract point of view, we can just ask, so if we take many instances of the problem, how hard is it to solve any of them? To solve one that you choose yourself. So now the game is no longer you get X, you try to solve, you try to find the solution. Now the problem is you get many X, X1, X2, X up to Xn, and N can be a huge number. And what your task is to just solve one of them, to find a solution for one of those. You can choose which. So this is a potentially easier problem, right? We have kind of a larger attack surface if you want to. So you get more opportunities, you get more possibilities to solve something. Okay. And the question is, how hard is this? Let's call it P to the N any. How hard is this problem P to the N any? Is it T epsilon prime hard for maybe the algorithms with the same runtime? Maybe can we say something about that algorithms with the same runtime have a larger chance of solving that problem? Or maybe is there a similar probability to solve that problem within a certain runtime? So it's not immediately clear how this relates, right? So potentially it's just easier because you have more possibilities to solve something. But is it really like properly easier? Is it much easier? So that is not clear a priori. So there's a fine print here. Please don't think about this in an asymptotic way, not because it's not possible, but because then it gets complicated how these runtimes and probabilities scale in the input length of this algorithm. So think about it maybe really relative to concrete numbers, t prime and epsilon or epsilon prime. Okay, and this is not at all obvious how to answer this. There's a general result that I want to present, and this is the most technical slide, and then it's getting less technical again. There is a general result that says that this may be more realistic or maybe more useful p to the n any problem is, yes, it is possibly less hard, but it is not much easier than the one instance version. So the proof idea for this is we can show that if there's a way to solve this p to the n any problem with a solver A, then we can also construct a solver that solves the potentially harder problem P, the original one, where you just get an instance X and you're supposed to output a solution for X. And again, so this is the worst part now. The proof idea is very simple. You just try to turn this solver that takes many instances, gives you a solution for one of them. You try to turn this into a solver that takes one instance of the problem and outputs the solution for that one instance. And what you do is just you internally kind of set up or simulate an environment just like for the many-time solver that needs to have access to many of those instances. And you just make up the other instances yourself. You just embed what you get as input, this X, you just embed it as one random instance of those, and then you hope that the adversary A chooses to solve that instance that you embedded and that you just slip in there. And that happens with a probability of 1 over n if you do this uniformly at random. And so what comes out of this is if this A succeeds in inverting or in solving a problem, the problem p to the n any, then with a probability of 1 over n, this A prime, will succeed in solving the original problem with one instance. So we have, read this here with probability 1 over n. You have just guessed which instance A solves later on. And so this allows you to turn, in principle, any solver for the many instance problem into a solver for the one instance problem, although you take a hit in the success probability. And that hit means that the P in any problem is at least about t comma n times epsilon hard, where n is the number of instances. So it's a bit less hard, maybe. But at least we have like a lower bound for hardness. This means that p to the n any is not much easier than the original problem P. And this is really the P, again, the P to the n any problem. This is the problem that we're interested in an application at the end of the day. So, and this factor of n can be annoying if it's a huge factor. So this can occur in applications again. So you can have n in the order of billions. And then you do not want this problem p to the n any that you're really interested in to be too easy. You don't want it to be like this n times epsilon. The guarantees shouldn't be too weak. But that just gives us a lower bound for hardness. So you could also ask, is this lower bound tight? So is that maybe, are there interesting problems for which this p to the n any is really problem easier than the original problem P, or maybe are they of the same difficulty? And that very much depends on the problem. For the problem I started with, the factoring problem, basically we don't know. So that's a big open problem. We don't know how well factoring scales in the number of instances that you get. it could be, for all we know, it could be that there may be easy instances X. So that means easy numbers, which you can factor easily. For instance, if we know that P and Q are not too far apart, if they are close, then there's a relatively simple method to factor the corresponding X. Of course, I mean, if P equals Q, then it's trivial. But even if P does not equal Q, then the product can be relatively easily factored. And so if there are subsets of easy instances X, then the likelihood to hit one among a huge number of instances grows. And so it's a bit like Russian roulette. You just get lots of instances and you hope that one of them is easy. And if there's one easy one among them, then you just attack that. And that means that it could be, we don't know, again, if there are such instances exist for factoring, or if there's really like sufficiently dense set of such easy instances. We don't know what the situation there is, but it could be, we cannot exclude that. And that would mean that the problem P to the n any is really much easier than the problem P. However, for other problems like discrete logarithm, even if we get many instances, so if we get many instances of the form g and g to the x, then this solving any one of those instances is not easier than solving one instance. So this problem, discrete logarithm, scales in a much better way. So if solving one instance is hard, then solving any out of many instances is not really easier. It doesn't help you to have many instances. So in that sense, discrete logarithm, or this problem of computing discrete logarithms, scales better than, at least as far as we know, than factoring. And this also means that for discrete logarithm, we can actually prove that there are no easy instances. Random instances like the one that you get in one instance case are really the hardest. All of those instances, in some sense, all of those instances look alike, like a brick in a uniform brick wall. Right, and now going back to cryptography, so this one just like, let's say, theoretical musings or theoretical observations. Back to cryptography. So how are such hard problems, the one-time problem or the many-time problem, useful? When we try to build an encryption scheme from such hard problems, then what we usually want to show is that if there's an adversary that breaks the encryption scheme, an E breaker A, so let's say the encryption scheme is called E, and if there's an encryption scheme breaker A, then we hope to turn this with a security reduction, we hope to turn this into a problem solver A prime. And this means that breaking the encryption scheme is just as hard as breaking or as solving the problem P. So there are, in fact, encryption schemes where we can show that if there is an adversary that in some definition of breaking the system breaks this encryption system, then we can turn this adversary into a factorization algorithm. So there are such examples of such encryption schemes, and that's in fact what we typically, at least in the literature, in the academic literature, what you typically try to show. If you want to propose such an encryption scheme, you basically need to have a security reduction to a reasonable assumption, such as the hardness of factoring. Of course, if P is somehow quantitatively harder, then E is secure against a larger class of adversaries. So this is really like a direct connection between adversaries on the encryption scheme and problem solvers. However, this provides only security, if you do this, then this provides only security of one instance of an encryption scheme in isolation. That is typically what these reductions do. So you have one person using an encryption scheme one time, and you can show that this in isolation, if there's an algorithm that somehow breaks this one ciphertext that finds a corresponding plaintext or does something else, distinguishes it from random, then you have some algorithm that solves your factorization problem. However, again, that covers only one instance. Sometimes, however, we can show that for many instances of the encryption scheme, let's say for a more realistic setting, where there's many people that use the encryption scheme for lots of times, then we can have one of those P to the N any solvers A prime. So you can also relate the security of many instances of an encryption scheme to one single problem. However, that single problem is this funny problem that also dealt with many instances. That is in fact often possible to show. That something more realistic, of course, relates to a larger version of the underlying problem. In some sense, it's like a photocopier where you can copy many instances of the encryption scheme, and you copy this correspondence. And for some types of security, we don't know how to achieve that. So there are also exceptions, but this is often possible. So now let's say we have this situation where we have an encryption scheme and we have many users in that encryption scheme that maybe use the encryption scheme many times. So something like you're communicating with your mobile phone. And using, of course you would use a secure messenger. And then you have an adversary that attacks maybe any user. And the guarantee is that if we have such a correspondence, then we can show that, like before, we can show that any adversary that attacks such a single instance out of many of an encryption scheme must solve a factorization problem or something similar. What we would do here is we would try to translate that setting into a setting where we have many instances of a hard problem. We try to embed those many instances of a hard problem into this many user setting, and then we try to. So maybe I should have even put those boxes on all of the arrows here. So maybe you even embed the problem into each single ciphertext, and you could translate an attack on that encryption scheme deployed. You could translate it into a problem solver. However, it's one of those P to the N any problems. So it's one with many instances. That was to motivate that this P to the N any notion is really a useful notion. So the story so far is that hard problems in general are useful for cryptography, and the many-time hardness, as in the form of the P to the N any problem, is even more useful for cryptography because it allows you to look at more realistic settings. Some problems, like the discrete logarithm problem, are naturally scalable and many-time hard in this sense. And for others, like factoring, we simply don't know. So for the last part of this talk, I will talk about a particularly nasty cryptographic challenge. So a particularly nasty setting in which we don't have such a, well, if you want to call this a success story, in which there is no success story like this. So, but before, do you have any questions? Was there anything about this part of the talk? Oh, okay, maybe you're all intimidated. I like to think you're rather, I like to think that you're intimidated by the recording, then that there is no question or that you're half asleep. But okay, so let me continue with this really hard problem, and this is currently it's a challenge. So the setting, let me set up the stage first and describe the setting. So the setting is we have a public key encryption scheme. So I'm assuming you have heard the term public key encryption scheme. So it's just one where you can encrypt with a public key, and for decryption you need a secret key, and those fit together in some sense, of course. So we have many senders and one receiver. So the green blob here is the receiver, and the blue blobs here are the many senders. So let's say that all of those senders, obviously they encrypt something, then they send it to the receiver, to the single receiver. Let's call the ciphertext here C1, C2, C3, and so on. They use randomness Ri. So there's an encryption algorithm that takes, of course, the public key of the receiver, so the public key of the green guy here, and the message, of course, and takes also random points Ri. And that is also something that is very typical. Secure encryption schemes need random points. So they need an encryption, well, not really function, but they need a way to encrypt an encryption algorithm that does not associate the same ciphertext to the same message all the time, because otherwise it would be very easy to check if you have a certain message encrypted. So you really need it. We need this randomness RI here. So the messages MI may be correlated. That means that, think of it like this. So maybe those are base stations that send some kind of measurement results to the receiver here. So that means that the measurements or the messages that are encrypted here, they may follow some correlation. Maybe it's different angles on the same thing. So there may be some correlation among the messages. They are not independent, but they are chosen from some kind of joint distribution. And then they're all encrypted. They're all sent to the one receiver. And the model here, or the question that we ask is, what if there is an adversary that goes around and just corrupts or just opens up certain senders or certain ciphertexts that are sent? So there is an adversary that can basically, first of all, observe all of the ciphertext CI and then point to individual ciphertexts and learn the corresponding message MI and the randomness RI. The goal of this is that the uncrypted messages, so the ones that the adversary did not point to, they should remain as secure as possible. I'm not going to define what secure as possible means, but it should be like a natural thought that if you have lots of ciphertexts and some adversary goes around and opens up or asks to have some of them opened up, then the ones that are not opened up, they should intuitively remain secure. So you should not, the adversary should know nothing more about them, as the adversary, of course, learns already through the open messages. So that's the setting. And our usual strategy to prove security, to show that the only way for an adversary to do something nasty is to solve an underlying problem. The usual the usual strategy to show security would be to turn the setting, to draw a box around the setting, turn the setting into a problem solver. So you get many instances, potentially a lot of instances of a hard problem, like with this P to the NN thing. And you try to embed those instances somehow. You try to formulate these ciphertexts with those instances such that if an adversary, let's say, solves one of those or opens up, learns something interesting about one of those ciphertexts that are not opened, then we can solve the underlying problem. So we can have a solution here that opens one of those boxes. That would be the natural strategy. However, that strategy doesn't work. So the problem with this is that the adversary here may, in this particular setting, as we said, points to particular ciphertexts or users and opens up or asks for these random coins and messages. So you don't exactly know where to embed those challenges. You don't know where to embed those instances of the problem that you get. If you embed them in the wrong place, then you do not know what the adversary would learn through corrupting them. So you cannot really simulate the whole, you cannot really draw that box anymore. And on the other hand, if you embed them into too few places, then the adversary might do something in the end that doesn't tell you anything about the instances here at all. Because the adversary may attack maybe some part of the system that has nothing to do with the instances here that you want to embed. So this problem is easy, in fact. So we know how to solve this if the corruptions don't leak this randomness, but only the message, or if the messages are not correlated. So then we can apply techniques, and we know how to solve this. But currently, we simply do not know how to solve this, and standard notions of security for the encryption scheme do not imply security in this setting if both the randomness here is revealed and also if the messages are correlated. So that is simply an example of a problem that, from a theoretical point of view, is very simple to describe and very easy. It looks very easy, but it's actually super hard to solve. It is super hard to give an encryption scheme, to construct an encryption scheme that is secure in this setting. And the best solutions are, in fact, quite inefficient. This problem is not understood well enough. So how do we deal with such nasty problems? Sometimes we have problems where our usual toolbox of tools does not work. So there's nothing in our toolbox that that really seems to solve that problem. So what do you do in those cases? You can solve the problem in another way. You can find practical solutions that maybe are the most realistic ones if you have that problem, if you encounter that problem in practice. You could try to use secure hardware so the randomness is not leaked. You could solve the problem on a protocol level, so you could try to circumvent it. Instead of encrypting, maybe you ask people to do some more complex handshake protocol with the receiving station. So you use it by just circumventing the problem statement in some sense. You could also just ignore the problem, because what I just said just means we don't know how to derive security guarantees. That does not mean at all that there is an attack. We don't know. We just cannot give security guarantees. So from a practical point of view, this may not even be such a big deal. This may not even be a problem, because we can perhaps relatively easily circumvent it or maybe even ignore it. It doesn't mean that anything breaks. From a theoretical point of view, however, it's super unsatisfying, because there's this barrier, we cannot prove anything, but at the same time, we don't even know if it's an issue in practice. Yeah, so we can use heuristics, there's something known, or funny assumptions, but that is kind of cheating in some sense. And what happens next? What happens in this situation if you encounter something like this in your life as a researcher? That very much depends on your motivations. So again, you realize I'm zooming out again. One thing you could do is just try to study the problem. And maybe you're annoyed by the fact that there seems to be a technical problem, you didn't really understand it, and so did no one else. And you try to spend a lot of time. You try to spend a lot of just effort and try to solve that problem. That's actually my own choice. That's what we did. And this has led to a number of interesting papers. And even then, even after like more than 10 years of looking at the problem, staring at it, we do have much better solutions than before, but they're still not practical. So in some sense, the situation right now is still not completely satisfying. There are many open questions. And I wouldn't claim, so there's a paper which is just about to be published in a few months, or it appears in a few months, and we're very, very happy with the result, but still it doesn't resolve the question. That would be lying. So it's not completely satisfying, but I would say that by now we understood the problem much better than before. So 15 years ago, we knew very little about the problem. Now we know much more, or in a much better way, why it's hard. So there's a complete open research question, basically solve that problem. Construct an efficient or a compact selective opening secure, that's what I was talking about, that is just the name for it. Construct selective opening secure encryption scheme from group-related assumptions. That would be one thing that is completely open. That could be a game changer, but I have no idea whether this is possible or not. Or maybe you could show that it isn't possible. There are also sometimes questions for which you can show that current techniques fail, or in a certain idealized model, maybe this question is simply unsolvable. There is no reduction that would show security. Sometimes you can show that. That is also, then at least the problem is solved. Maybe that doesn't help you in practice, but at least now you know. Okay, so I'm already at the last slide. So what's the takeaway message here? So most importantly, I would like to transmit the message or transport the message that there are many legitimate research attitudes. There's the ones where you're really motivated by the application, that's completely fine. There's also one where you try to understand the structure, that's also completely fine. And it's important that you find your own. Don't let anybody tell you why you're doing something. You should like it. And cryptography, and maybe a slightly more technical thing, cryptography thrives on hard problems, and you need to play a little with them to understand what's going on. Maybe from a theoretical point of view, for me personally, cryptography is to define, translate, and use those problems. And there's many open questions in the area. Even for relatively simply looking topics or problems, there are deep questions that still need to be resolved and are poorly understood. what I find personally even more technically now, what I find personally very challenging are adaptive corruptions, or settings in which you have an adversary that just like tampers in a very adaptive way with the system or with what's going on. And that makes it very hard from a technical point of view to connect a very static problem like factor this large number, or maybe compute the discrete logarithm of any of those numbers here. Something that is very static, so you get a bunch of instances and you're supposed to, I don't know, embed them into your system somehow. That is just technically very challenging to connect this or to embed this into a dynamic system. And again, so that's a very I should not go to that slide. Yeah, so that's actually all I wanted to say. So I hope I could at least justify theory a bit more for you. So yeah, that's it. Thanks for your attention.